Hello, good evening everyone. My name is Akhil, and to those of you who are watching this for the first time, I am a PhD student from IIT Madras. We do weekly live problem solving sessions for the course Machinery Fault Diagnosis and Signal Processing, where we solve assignment questions which are similar to the assignments which you need to submit, but not the exact questions. We meet every Saturday from 7 to 9 p.m. and you can find these sessions uploaded in YouTube also, the recordings of this. If you search for machinery fault diagnosis and signal processing live sessions, you should be able to find. Okay, so by default, keep yourself as mute, and if you have any doubt or question, you can unmute yourself and ask. Great. So let's begin the session, today's session. We'll be looking at week 4. Okay. So some of the concepts from week 3 will also come. So this is one such question. Fourier series expansion of a periodic even function contains. So any idea on what exactly is Fourier series expansion? Either Rajesh or Samir. Any ideas on what exactly is Fourier series expansion? Okay. Yeah. So in Fourier, what he has found out is one of his inventions. If you have any function, you can convert that into a sum of series of sine and cosine functions. So let me give one basic generic function. So a function f of t, any function can be written in this form. So this is we have discussed in last week also. I'm just repeating it here. So any function you can write it in terms of sum of sines and cosines. Okay. So if you write it in that form, that is called the Fourier series expansion of a given function. Okay. Now in this question, what we are discussing is if we have an even function, periodic even function, then what are the terms that it will contain? So as you see, Fourier function has a constant, a cosine terms, and sine terms, right? Yeah. Now let's see if each of them will be odd or even. So what exactly is odd or even is a function is odd if f of minus x is equal to minus f of x, and even if f of minus x is equal to f of x. So for example, take function f is equal to x. Okay, f of x is equal to just x. Is it even or odd? Can anyone tell me? Will this function be odd or even? Just f of x equal to x. Even. Okay, so let's see. So f of x is x. What is f of minus x? Minus x. So which is same as minus f of x. So then it is odd function, right? And not even. Now similarly, if you look at f of x is equal to x square, what about this? Will this be even or odd? So if you replace x with minus x and whole square, then it becomes again x square, which is same as f of x. So f of minus x is same as f of x. So such a function is even function. Okay. Now Now let's see if cos is even or odd. What is f of minus x? So cos of minus x. Can anyone tell me what is cos of minus x? No. Cos of minus x is just cos of x. Sin of minus x is minus sin of x. Okay. This is because let's say 0 to 90 degrees and minus 90 degrees. So first let's look at cos function. Cos 0 is 1, right? And cos 90 is 0 and cos minus 90 is also 0. So cos is like this. So if you see, for minus negative values also cos is actually positive only and it is symmetric. So cos of minus x is also cos of x. But if you take sin of 0 is 0 and sin 90 is 1. And sin minus 90 is minus 1. Okay. So sin of negative x is minus of sin x. So it is odd and it is even. Okay. Now your periodic function is f of minus x is equal to f of x. So even function. So if you are expanding an even function, in that expansion also you should only have the corresponding even terms. Okay. So the cos is even and sin is odd. So sin terms shouldn't be present, only cos terms should be present. So is that clear? Yeah. So if you are yeah okay. So for even function, as cos is even and sin is odd, only cos terms will be present. And for an odd function, it is exactly opposite. Only sin terms. Okay. So we have discussed this in last week's session also. You can maybe go through that. It might help. So is this clear? Based on even or odd functions, you can guess which kind of terms are present in the Fourier series expansion. Okay. So let's move on to, is this point clear? Samir and yeah, okay. And I think Rajesh, it's clear to you already. Yeah. So let's move to the next question. Yeah. So which is a famous function used to convert signals from time domain to frequency domain? Yeah. Can one of you answer this or both of you? Yes. So what is the full form of FFT? Yeah. So fast Fourier transform is actually an algorithm to perform the Fourier transform on a given data, and it can do much faster than a normal Fourier transform. So the actual function is the Fourier transform. Okay. And here you shouldn't answer if it's given, if let's say fast Fourier transform, discrete Fourier transform and Fourier transfer. If all three are the options for this question, you should answer Fourier transform. Okay. So the answer is Fourier transform is the famous function, which in reality, like in the real world, which is used so much in the industry, and it is one of the most important mathematical functions in the world actually. So the simple way or one of the ways to convert directly the data to frequency domain. So omega is your frequency and f of t is this is the time based signal. Okay. So if you multiply the given signal with e power minus I 2 pi omega t. So you know the in notations, right? E is the exponent and I is the imaginary number. So this is one of the ways of representing complex numbers. Multiplying the real time signal with a complex number and then integrating the entire thing from infinite over the infinite regime minus infinity to plus infinite. You can actually get the frequency, you can convert the function to frequency domain. So this is in frequency domain and this is time domain. Okay. So this is what Fourier transform does. A given time domain signal is converted to frequency domain in this format. Okay. Is this clear? Yeah. So now let's see the next question. Yeah. And you don't have to do all these operations on your own. Now there are MATLAB and this Python tools already, which can actually, if you give them the data, they will give you the frequency response automatically. Okay. So next question. What is discrete Fourier transform? So we have seen what is Fourier transform. Now what is discrete Fourier transform? So in real life, the data is not actually analog, right? You don't have an analog function like the output as sin x or anything. You have discrete data points as a function of time. You have discrete data at different time intervals, right? And not the analog data. So to convert a discrete time domain signal to a frequency domain signal, we have the discrete Fourier transform. Okay. So it converts a finite sequence of equally spaced samples of a function. So this is like, let's say you have a sine function and here you are only looking at 3 periods, right? Okay. So but in the Fourier transform we looked at from minus infinity to infinity, so the entire domain. But in real scenarios you don't have the infinite domain. So in real scenarios you have only a specific domain. So here in and one more thing is you don't have the data at every time instance. You only have at specific time intervals. So that's what I mean here. Converts a finite sequence of equally spaced samples of a function. So we're actually sampling at these data, these time instances. Okay. So of a function into a complex valued function of frequency. And one more thing to notice is the Fourier transform actually gives you a complex function and not a real function. So it's your job to again differentiate the real parts and complex parts from the frequency Fourier transform and use based on the need. Okay, so this is one example where analog signal is sampled at digital time points with every delta t time instance and converted to FFT. Okay, so here FFT is used, but we are actually talking about DFT. So the difference between them is how do you convert the signal? What is the exact algorithm? Okay, yeah. So that is the next question. Can you tell me what is the difference, exact difference between FFT and DFT? Any idea on that? So we have seen in FFT, you need to do this multiplication and then integration, right? Okay. Now, if you do the normal DFT algorithm, you would have to perform n square number of operations. Let's say you have a n data points. You need to do n square number of calculations or number of operations. But FFT, you had to do only so this is a FFT is basically doing the Fourier transform, but in a little bit optimized and efficient way, where they reduce the actual number of calculations needed. Okay, so that is FFT, fast Fourier transform, and DFT, discrete Fourier transform. So is this clear, Rajesh and Samir? Yeah. And in real life, we actually use FFT mainly because you'll actually save a lot of computational time. And how much computational time, I think we will see in the next question, one example. And yeah, so I can give you one more example, exact equation here for the DFT. So for normal Fourier transform, we have seen this, right? This is when analog signal. You have the exact function, but for the digital case, this looks something like this. Okay, so this is where that number of operations comes from. So here this is a complex number that is multiplied with the signal and then added up. So that n square number of operations comes from this actual this term. Okay, so this is how you deal with the digital data or discrete data. And fast Fourier transform, you basically reduce how many number of operations you need to do to perform this integration or summation. So now for a data set of 1024 points, okay, you have almost 1000 points. How many orders of magnitude will FFT be faster than DFT? So can one of you tell me how can we calculate this? How much faster one would be than the other? Any idea from this? Okay. Uh, so because we know that DFT requires operations of the order of n square, so you actually need 1024 square number of operations to be performed, right? and this actually equals to 1000 square, so almost 10 power 6. Do you guys agree with that? Now, if you have FFT, order of n log n, so you need to do 1024 log 2 of 1024. So which is equal to, what is log 2 of 1024? So 1024 is actually 2 power 10. So this becomes, so this is almost 1000 into 10, 10,000. So 10 power 4. So you see in FFT, so let's say each operation takes a second. It's actually much more faster. So you need 10 power 4 seconds, and in DFT 10 power 6 seconds. So FFT in this case is actually 100 times faster. Do you guys agree with that? Is there any doubt in this question? How many times will one be faster than the other? Samir and Rajesh? Okay, okay. So now do you understand why FFT is that widely compared to DFT? So because if you have, let's say, just 1000 data points, FFT is 100 times faster. So imagine when you have 10,000 or 100,000 or a million data points, which is more closer to the realistic operations in factories. Okay, so that's why we use FFT, and yeah. No, DFT and FFT are basically two different ways of doing the Fourier transform to the discrete data. That's it. In DFT, you follow the standard procedure. In FFT, you do some intelligent manipulations of the operations. You frame it in a different way, but you exactly end up at the final same answer. You frame it in a different way so that you don't have to do the that many number of operations. That's it. Both at the end are giving you the Fourier transform only. Okay, yeah, both will convert time domain signal to frequency domain signal, but FFT does it much faster than the standard DFT processor. That's it. Yeah. So the next question, for a non-stationary signal, which of the following is best advised? DFT, FFT, STFT. Can one of you tell me what is non-stationary signal, or what is stationary signal? And do you know what is? So we have seen what is DFT, what is FFT. Do you know what is STFT? Samir, are you saying something? I'm not able to hear you. Okay. Yes, yes. So this is an example. So if you see in the starting, the spacing is more between the two waves. That means the time period is more. But if you see at the ending, the signals are very fast. That is, time period is very low. That means here frequency is high and here frequency is low. So a signal where the frequency changes with the time, that is called a non-stationary signal. Can you tell me, will sine wave or cos waves are the examples of stationary or non-stationary signals? Basic sine and cos. So if you write sine function, you just write as this way, right? So you only have one frequency. So it is an example of stationary signal only. Okay. But you can write functions which can show these non-stationary signals. They might not be sine or some different forms. So where the frequency changes with time, that is called a non-stationary signal. And in that, for that signal, if you do FFT or DFT, you can't estimate the frequencies that accurately. So for such signals, there is something called short time Fourier transform. So here what we do is, as we know the frequency is changing, we divide the signal into different sets and perform FFT on each set. Okay. So we will get frequency function in this domain, again in this, again in this. So different FFTs we need to do. Okay. So that doing this is called short time Fourier transform. Okay. So is this clear? Why you need to do short time Fourier transform for non-stationary signals? You can just open MATLAB if you have access to, or if you don't have access to MATLAB, you can just try it in Python. You can generate these sine functions and then try to do this FFT, STFT and all this data. Okay. And actually, I think I will show in the next class, maybe using MATLAB, some examples of this FFT and STFT. And regarding the website, I will search for some. Right now, I don't know. Maybe some websites where they give this beautiful data to and let you understand this Fourier transforms better. Okay. But up to this, is it clear? Now, short term Fourier transform. Yeah. Okay. Thank you. Yeah. So. Hmm. So we have discussed what exactly is Fourier transform, and then discrete Fourier transform, and the number of operations, and then how FFT is faster than DFT, and then which is suitable for non-stationary signal. Okay. Yeah. Now let's move on to the next question. Yeah. I'll read out the question and I'll give you 1-2 minutes to think about it. The error arising from using lower sampling rate than the frequencies present in the system is called. Yes, correct. So it's called aliasing error. Yeah. Yes. So this is one example to see that. So the black wave is actually the real wave, but you are only sampling at this dots, black circles. So when you look at the sampled data, it looks like a sine wave, but if you see the time period, sine waves time periods which you extracted, and then if you do the frequency from the extracted data, let's say this uh, okay, let's say this time period is 10 seconds. So 1 by 10, you will see the frequency as 0.1 hertz. But if you see the real signal, its time period is only this much, and which is equivalent to 1, 2, 1, 2, 3, 4, 5. Yeah. So 2 seconds. So the real frequency is actually 0.5 hertz. Okay. So a frequency of a signal 0.5 hertz, when you sample the data from that signal, because your sampling rate is not high enough, and the frequency you got was only 0.1 hertz instead of 0.5. Okay. So this is called aliasing error. So this comes when your sampling rate is lower than the frequencies present in the system. Okay. So is this clear? Aliasing error. So it's always advisable, if you know the frequencies in the system, you should your sampling rate should be at least twice the frequencies in the system. So we'll see that examples in the later. But is this clear? The real frequency is 0.5 hertz, but your sampling rate is bad. You only got frequency of 0.1 hertz. Okay. So this became this. That is why it's called the aliasing error. Okay. Yeah. So the error arising from using lower sampling rate than the frequencies present in the system. Yeah. So now to prevent signal aliasing, the signal should be sampled at compared to the maximum frequency in the signal. Can any of you answer this? Yeah. So it's actually, you should sample at least 2 times more than the maximum frequency in the system. Then you won't miss any frequencies present in the signal. Okay. So in this case, because the frequency is 0.5 hertz, yeah. So if you had sampled at least 1 hertz, that means here, if your sampling was at least that strong, then you could have ended up with that 0.5 hertz just there, okay, at the end. But that is also not advisable, but that is the least you can go to, greater than or equal to 2 times the maximum frequency. Okay, is this clear? So we have an example of this. Yeah. So yeah, delta t is the sampling interval. So the sampling frequency is 1 by delta t. So this is the real data, and the data, the circles are the sampling points. And for that you perform the FFT. So in that FFT, this is what the frequencies you will get. Okay. And the frequency resolution, delta F, which you would get is 1 by total time period. Okay. So the frequency resolution is only a function of the total time period. But if you see the frequency maximum, yeah, this is a mistake here. So total time period is n into delta t. Okay. So the frequency maximum that you can get is actually 1 by 2.56 into 1 by n into delta t. So see, it's a function of what is your sampling time interval. So if you decrease your sampling time interval, that means if you increase the number of data points in the same time period, then you can keep getting better and better frequencies. Okay. So this 2.56 is the more realistic one than 2. So greater than or equal to 2, but in reality people actually go till 2.56 only. Okay. Is this clear or it was little confusing to three of you? Uh, if you have any doubt, we can discuss. If it is clear, I will move on to the next point. So at the end, the conclusion is, if you want to prevent the signal aliasing, you should sample the data at 2 times the maximum frequency in the signal. That's it. Okay. Yeah. I think with that, I think you guys can answer this question on your own. So here we have a signal which contains frequencies of 10 Hertz, 20 Hertz and 100 Hertz, and they are asking what should be the sampling frequency. Okay. Yeah. I think if you have understood the previous discussion, you should be able to answer this. So I'll give you a minute to come up with an answer. Yeah. Why 200 Hertz? Yes. So whenever this kind of questions come, first you note down the maximum frequency in the signal. So here max of 10, 20 and 100, so 100 Hertz, and your sampling rate should be greater than or equal to 2 into f max. So sampling rate should be greater than or equal to 200 Hertz. That's it. So as simple as that. Okay. Yeah. So this you will get questions like what should be the inquest rate of sampling. So that is also similar. Yeah. So this was clear. Now a similar question but framed in a different way. What should be the sampling frequency for this signal? As a function of time, it is given as 15 sine 3.14 t plus 10 sine 628 into t. Can you tell me now? It will need some little bit calculation, so I'll give you a minute or two to try it out. If you got the answer, you can unmute and say your answer. So I'll give you some options to help you along. Yeah. Okay. Any other answers? Samir, what about you? Okay. Okay. So Rajesh, this is actually the wrong answer. I'll tell you why. So when you have the sine functions, so a sine general form is a sine omega t. So this omega is not the frequency. The actual frequency is so the frequency is omega by 2 pi. Okay. So here x of t has two signals. For signal 1, the frequency is 3.14 by 2 pi. So pi is equal to actually 3.14, so 1 by 2, 0.5 hertz. And the second frequency it has is 628 by 2 pi. So 628 you can write as 2 into 314, so 3.14 into 100 hertz. So now what do you think should be the answer? Yeah. So this is the answer. So you see, even though you are able to answer the previous question where the frequencies are directly given, you could be like made to confuse if they give the question like this. Okay. So here two things. First, you need to know this formula to convert from the radial frequency to real frequency, and then two times the maximum frequency available. Okay. 200 hertz. Any doubt in this? Okay. Now let's move on to the next question. So calculate the beat frequency when two signals with frequency values of 100 Hz and 103 Hz exist in a system. So any idea on the beat frequency? I think we discussed this in the last week also. Yeah. So when you have signal with two parts with very close frequencies, then you end up with a signal of this sort. Okay. So this is called signal beating. So for that signal beating, if you want the frequency of this phenomena, okay, so that the frequency of this is the frequency of the beating frequency, it's called. So it's just the difference between the two frequencies which you consider. Okay, so beat frequency here is a difference between the two frequencies. So 100 minus 103 So 3 Hertz. Okay. So is this clear? Beat frequency. Yeah. So let's move to the next question. Again, beat frequency. If the signals in the system are A 100 sin pi t and B cos 104 pi t. Yeah. So this is the two concepts which we discussed in last two questions. So you need to combine these two. I'll give you a minute to come think of the answer. So first you need to estimate the frequencies of each and then the difference. So can you tell me what is the frequency of the first signal here? Any of you? Omega by 2 pi, right? So 100 pi by 2 pi. So first signal's frequency is 50 Hertz. And what is the second signal's frequency? Now what should be the beat frequency? Yeah. So is this clear now? Now I think if any question they gave in terms of beat frequencies or the sampling rate, I think you guys will be able to answer. Okay. So 2 Hertz. Yeah. So any doubts up to this point? We have discussed the beat frequencies, sampling rates, and aliasing error. Okay. Yeah. Let's move on to the next question. Yeah. So have you come across something like this? Window functions are applied to minimize leakage error or digitization error or aliasing error or none of the above. Okay. Samir, what about you? You have any? Okay. So the correct answer is leakage error. Uh, so we all know what is aliasing error. That comes because of lower sampling rate. And the digitization error comes because your resolution is not enough to capture the very tiny amount of signal which is coming. Okay. So even if you have very small signal, if you apply window functions, nothing is going to happen to that small value. So window functions won't help in digitization error. But leakage error comes because when you are extracting the data, there could be some sudden breaks, and that could actually lead to something of this sort. So if you see here, without any leakage, the data is very continuous. But when there is some leakage, you can see this, the data is continuous, but it is not as it should be, right? There is some, this part repeating here. Can you see? Okay. So this is the leakage. Now for this, there are some things called window functions. So what they do is basically in this window they try to make in the entire window it starts from 0 to ends at 0. Okay, so that helps in minimizing these leakages. And there are different window functions also that you will see maybe in the text. So window functions are actually help to minimize the leakage error and not the distribution error or aliasing error. Okay, is this clear? Okay, yeah. So what is the modulation of a signal? Can any of you tell me what you understood by modulation of a signal? Right. So have you ever come across this word modulation? Any of you? Okay. So you have come across it, but you don't know exactly what it means. Okay. So in general, yes, yes, yeah, frequency modulation and there is amplitude modulation also. So what it exactly means is, in general, when you are transmitting the signals, instead of sending the signal directly, you modulate it with something called a carrier wave and then send the signal. Okay, so this adding that signal to a carrier wave or multiplying or doing modulation with frequency or amplitude, this part is called modulation. So in general, uh, when a signal is transmitted, it is mixed with a carrier with another and one more important point of this carrier wave is it's a much higher frequency than the signal which you are transmitting. Okay, so you mix your signal with another high frequency sinusoidal signal which is actually called carrier signal. This is called modulation. Okay, and there are two types. There is amplitude modulation and frequency modulation also. Okay, so this the reason why they added to mix with another high frequency signal is this helps in the data to be transmitted without losing any data actually. So if you just send the normal low frequency signal, there is a possibility that you may lose some part of the data. But when you mix it with some high frequency signal, then that loss will be negligible. That's why they do this. Okay, so that is called modulation. Now, yeah, next question. Yes. So when you do this modulation, you're actually losing the real signal, right? It becomes a modulated signal. So in that case, to obtain the actual frequency of the real signal, so you have the actual signal, which is called modulated signal, and you have the carrier signal, and you have the amplitude modulated signal or the frequency modulated signal. So you have these three signals, but you only care about the modulated signal because that is the real signal, and carrier signal is something which you only added. So you know the frequency of the carrier signal, and you only know the modulator amplitude modulated signal. So the final result. Now if you want to get the initial frequency, what you should do? So that is the question here. So the options are Hilbert transform, substrum analysis, just doing FFT, or none of the above. So any idea on this? Any idea? Okay. So there is something called Hilbert transform which actually helps in this. So we'll see one example below. So this is the amplitude modulated signal. So you have a signal, then you mix it with a carrier frequency in an amplitude modulated format, and then you got this signal. Now if you do FFT of this, you see you have peaks at three different points, 15, 20 and 25. Okay. So this 20 is the frequency of the carrier signal. So why are 15 and 25 coming? Because you mixed it with the real signal, modulated signal. But which is the frequency of the modulated signal? Which is either 15 or 25 or some different number? How do you know? You don't. So what you do is you run on this signal Hilbert transform. Okay. So Hilbert transform converts from time domain to time domain only. So this is time domain and then still converted to time domain. But doing the Hilbert transform gives you this envelope. You are seeing this here, the top black line compared to the actual signal. So this is the envelope. Okay. It's called. So now if you do the FFT of the envelope. Okay. So this is FFT of the envelope. Now you would get the frequency of the actual signal. Okay. You understood this? So what happened here was you have a modulated signal of 5 hertz. Okay. And a carrier signal of 20 hertz, and then you mixed them both to get amplitude modulated signal which had a FFT like this. There are peaks at 15, 20 and 25. You know the carrier signal is of 20 hertz. But what is the actual signal of the modulated signal? That you can't FFT directly of this signal won't give you. So you do the Hilbert transform to get the envelope, and then you do the FFT, then you get back the 5 hertz. Okay. Is this clear? Samir and Rajesh, is this clear? You can say no also if you want me to explain again, I will. Your voice is breaking. Mm, So I will explain it again. So first you have a signal. Let's say we call it signal A, modulated signal, and it has a frequency of 5 hertz. Okay, that signal you mix it with the carrier signal B of frequency 20 hertz. With that you got the signal C. Okay, now on the receiver side you only see C. Hmm. So receiver only gets this. Okay, so he got the signal C. Now the question is, how does the receiver extract the actual signal A? Okay, so that is the question, and he doesn't know that it is 5 hertz. He didn't do the modulation. Okay, so he doesn't know the 5 hertz and 20 hertz. So what you can do is, for signal C you perform the Hilbert transform. Okay, then you will get something called envelope, which in this graph looks like this. Okay, now if you do FFT of this envelope, then you will get frequency of signal A. Now is it clear? Sorry, I couldn't hear you actually, so can you repeat me again? Carrier frequency, yes. So if you do FFT of this directly, then you will get a major peak. So okay, yeah. So you see this is FFT of the signal C. So this peak is actually the carrier signal. So this way, first you will get the carrier signal frequency 20 hertz. Now you do the Hilbert transform on the original signal, you will get the envelope. On the envelope you do the FFT, then you will get the frequency of signal A. Okay. Yes, yes, yes. Okay. So this way you have both the A and B's frequency. So you know the information which was sent. You can decouple them now. Is this understood now? Is it clear to both of you, Rajesh and Sam? Yeah. Okay, thank you. Samir, is it clear to you also? Okay, okay, thank you. Yeah. So one more thing to notice, Hilbert transform, you are actually converting from time to time domain only. It's not like time to frequency. It's just converting from time to time. So that is also one thing you need to remember. Okay. So let's move to the next question. Yeah. To recover signals in time domain from a signal with poor signal to noise ratio and with large amplitudes of sidebands, which analysis is useful? Yeah. Can you guys guess this option? Now actually you know what is STFT and what is Hilbert. You don't know what is substrum, and you also know what STFT and Hilbert are exactly used for. So can you guess the answer for this question? Yes, yes. The answer is substrum. So understand this again. A signal with poor signal to noise ratio, that means it's very bad, and it has large families of sidebands. This is actually more closer to a realistic scenario when you're actually doing FFT of a gearbox or anything. Okay, so there to recover the real signal, we do the substrum analysis. So what exactly is substrum? I will give you the exact equation. Yeah. So see here what I am exactly writing. Pay close attention. Okay. So this is substrum analysis. So you see, first we have free time domain signal, real signal, and then we do the Fourier transform. F means Fourier transform, and here XX I have. So this is auto power spectrum which we discussed last week. I'll tell you exactly what it is. So first you do the Fourier transform. So the real signal, you do the Fourier transform first. Okay, and then you do the log of it. Okay, and then you do the inverse Fourier. Okay, so then this time domain signal here it is in frequencies, again as a function of frequencies. When you do inverse Fourier, it becomes again something like time but not exactly the real time. So this is called Q frequency. Okay, which is like time but not exact time, and it is called Q frequency. Okay, so this is called substrum analysis. You understood this now? So basically you do the Fourier transform and then do the log of the Fourier transform and then you do the inverse again. So then you would have then you would have the final signal. So which is the real signal which you want to worry about actually. It will remove all the noise and everything. Okay. And this fxx is basically, let's say this is your Fourier transform. Yeah. So you are only looking at the magnitude of the complex function. So as I said earlier, when you do the Fourier transform, you will actually end up with a complex function like a plus ib. And in fxx, we only care about the magnitudes. So if you multiply a plus ib with a minus ib, its complex conjugate multiplication, you would actually get a square plus b square. Okay. So that is what you use to do the log. Is that clear? To Rajesh and Samir, is this clear? Yeah. So, and this function is directly available in these statistical tools. If you give them the data, you will get out the substrum analysis. So, it's basically to remove the noise in the signal. That's it. Okay. Yeah, and it is also in a time-like domain, but not exactly time. It's called Q frequency, and it's not frequency. It is a time type signal, time domain only. Okay. Yeah. So this is substrum analysis. Yes. Next question. How do you differentiate the carrier and the modulated frequencies? Yes. So as we discussed, Hilbert transform is what you use to differentiate between the carrier frequency and the modulated frequencies. And subsystem analysis is to obtain the real signals from very bad signals. And DFT is a discrete Fourier transform, and inverse FFT you understood now. So inverse FFT you apply it on the frequency domain and you get back the time domain. That's it. So Hilbert transform is what you use to differentiate the carrier and the modulated frequencies. Okay. Samir, you also got that right? Yeah. Okay. Thank you. So the next question. Yeah. So the resolution for storing a signal which is ranging from -5 volts to 5 volts in a data storage system with 10 bits will be. Yeah. I'll give you guys 1 or 2 minutes to think about this question and then we'll see. So if you know the answer, you can spell it out, and if you know how to calculate it, also you can spell it. Any idea on this? Okay. Uh, so whenever you are asked about resolution, first thing you should calculate is the range. So range is the difference between maximum and minimum, right? So what is the range here? 10 volts. Okay. Now you have a data storage system with 10 bits. So if you have 10 bits, what are the possible number of values that it can take? Is 2 power 10, because in each bit there can be either 1 or 0. So let's take it like this, 10 bit, right? 1. So here you can have either 1 or 0, here 1 or 0, here 0 or 1. So for each bit there is a possible two possibilities, either 1 or 0, right? And in the second location also again two possibilities, third location also two possibilities. So like that 2 into 10 power possibilities are there. Okay. Now your range is 10 volts. This 10 volts you can store in 2 power 10 number of possibilities. So then what would be the resolution? Right? So what is 10 by 2 power 10? 2 power 10 I think is 1024. So this would be, let me see, 0.0097 volts. So almost 9.7 millivolt. Okay, is this clear how I calculated this resolution? So you can have values ranging with differences of almost 9.7 millivolts. So that means we can have 0, 9.7, 2 into 9.7, 3 into 9.7, like this. Okay. And lastly at the end you will have 10 volts. Is this clear? The resolution? Rajesh and Samir? Okay, okay, good. So the next question, a 12-bit data converter has a resolution of. So the options are in percentages. So you can take the range to be 1 and multiply it with 100 because you want in percentages. So can you calculate and tell me what should be the resolution here? Right? 2 power 12 is 1496, I think. So now can you guys tell me what would be the resolution in percentage for a 4-bit system? I'm hoping one of you will give me the answer. I'm not going to calculate this. Or can you at least spell me the procedures? What would be the first step? One of you? Rajesh? 100 by 2 power 4, so 100 by 16, right? Yeah. So 100 by 16, 6 point some percentage. Okay. Yeah. So that is how you can estimate the resolutions in a 12-bit data converter and a 4-bit. So yeah. Now the next question. Yes. To overcome the digitization error in the ADC process, which of the following is advisable? So do you know what is digitization error? Any of you? Increase the number of bits. Yes, that is correct. Uh, but first, can you tell me what is digitization error? So increase number of bits, that is the correct answer. Because we know what sampling frequency does, it helps in the aliasing error, and so it's not, it has nothing to do with the digitization error. So it's either number of bits and increase or decrease, that we will see if you know what digitization error means. So similar to the earlier case, let's say if you have a signal of range 10 volt, okay. Now you have only a 3-bit ADC, okay. So then what are the possible values here? So all filled with zeros, all filled with ones. What are the possibilities? Can you guys tell? So these are one. What are the other possibilities? 101. So similarly 011 and 110. So you only have 8 possibilities, right? So 2 power 3, 8. Yeah. So if you divide 8 volts by 8, 10 volts by 8, you would actually have 1.25 volt as the resolution. So when you have a resolution of 1.25 volts, but your signal has some signals whose value is less than 1.25 volts, what will happen to that? Okay, we'll start from 0. Let's say if your signal is like this, then what are the points that you can recognize? Will you be able to notice anything in this regime? No, right? So everything will be made as 0 only, right? Is that clear? So all of this would be 1 point taken as 1.25, all of this would be taken as 2.5 or something like that, like, or the average of these two, and all of this would be set as 0 only or 0.75 based on your this thing. So you see, the data which is smaller than the resolution, you are actually losing that. So that is due to the converting from analog signal to digital signal, digitization error. Okay, is that clear? What is digitization error? Samir and Rajesh. Okay. Now let's move to the next question. 20 and 21. Yeah. Which of the following errors are errors due to data acquisition? Signal aliasing, quantization error, or both or none? So yeah, this is the last question. I think you will be able to answer this question. Yeah. Yes, Samir. The answer is both. Yeah. Yeah. because signal aliasing comes when you are actually doing the sampling because of the sampling rate. So that is also that part of data acquisition. And quantization error is same as digitization error. It comes because you are not able to capture the values smaller than the resolution. So that is also part of data acquisition. So both occur because of the data acquisition only. Okay. Yeah. Uh, any doubts in today's discussion? So yeah, let me revise once everything so that we can close the session. Yeah. So today first we started with the Fourier series expansion, and yeah, and we looked at what will be the terms which will be present in the Fourier series if your function is only periodic, even, or odd. And we saw that if it is odd, then you will have only sine terms, and if it is even, you will only have cos terms. Okay. And next we saw that what exactly Fourier transform does, converting a time domain signal to the frequency domain. And if it is an analog neat signal, you can do this, where you need to integrate from minus infinity to plus infinity. But in reality, you'll only have a digital data uh, in a finite time interval. So that is called discrete Fourier transform. It converts a finite sequence of equally spaced samples into a complex valued function of frequency. Okay. Next, yeah. So this is for the discrete data, how you can obtain the frequency domain information. Okay. And next, yeah. So next we looked at how FFT is different than this discrete Fourier transform. In basically the number of operations you need to perform to estimate the frequency domain. Where we saw that DFT you require n square number of operations, but in FFT you only need n log 2 n number of operations. So because of this difference in number of operations you need, FFT is much faster than DFT, and for a simple case of 1024 data points, we saw that FFT is 100 times faster than DFT. Okay. Yeah. And then we looked at what is suitable for a non-stationary signal. That is the signal where the frequency changes with the time. So we saw that short time Fourier transform, where you divide the signal into multiple uh, slots and then do the FFT for each of them, each window. That is called short time Fourier transform, and that is more suitable. And we saw that what will be the errors which arise from the very low sampling rate. It's called aliasing error. Here we lose the frequencies which are present in the system. So that is why it's called as an aliasing error. That is basically a high frequency signal is denoted as a low frequency signal, aliased as a. And next we saw what to prevent this signal aliasing, what should be your sampling rate compared to the maximum frequency present in the signal. So your sampling rate should be 2 times more than the frequencies present in the system. And based on that we did some problems also. And in the same case we looked at a little tricky question where the radial frequency is given and from which you need to actually extract the correct frequency, and from that you can again get the sampling frequency what it should be at least. Okay. So should be greater than or equal to. So you can actually take much higher sampling frequencies, and higher the sampling frequency, better information you will get, but you need to store a lot of data. So there is a trade-off. And next we looked at the beating signal, and we saw that if you want to estimate the frequency of the beats, the difference in the frequencies will give you the beating frequency. And next we looked at a similar beating frequency, but here again we are only given the radial frequencies from which we need to obtain the actual frequency. Next we looked at what is leakage error and what is needed for to minimize the leakage error. And then we looked at what is modulation of a signal. So when you mix it with a very high frequency carrier signal, then you are basically doing modulation. And there are two types: amplitude modulation and frequency modulation. And to obtain the real frequency or the frequency of the modulated signal on the receiver side, uh, you need to first get the carrier signal, that is by doing the FFT of the modulated signal, amplitude modulated signal, and then you perform Hilbert transform on the amplitude modulated signal. Then you'll get something called envelope, and if you do FFT of the envelope, then you will get with the frequency of the modulated signal. So we saw that. And Hilbert transform is to convert from time domain data to time domain only. And next we looked at what you need to do when you have very poor signal to noise ratio and so many sidebands. That is to do substrum analysis, where after performing Fourier, you look at the magnitude of that, you take the log of that, and then inverse Fourier of that to get a real signal. Here the final signal is also in terms of time, not exactly time. It's called a Q frequency, which is similar to time but not exactly time, equivalent to time. Then we looked at again some questions on Hilbert transform to differentiate the carrier and the modulated frequencies. Then we looked at what is the resolution when you are converting a signal from analog to digital, and based on your data storage system what will be the resolution. So range by 2 power bit size, so 2 power n basically. And we looked at in terms of percentages if it is given, and we saw how what is the digitization error. So that is when your signal is actually lower than the resolution, then you will lose that information. So to avoid that, if you increase the number of bits, basically improve your storage system, then you can avoid that. And we finally went with this final question: what are the errors that occur in data acquisition? Some of them are signal aliasing and quantization error. Okay, yeah. So that is it for this week. Then any more doubts, Rajesh? No. Okay. Thank you, Rajesh. You can leave the session. We'll meet again next week. Thank you.